Okay, so now I'll share the screen with this nanomaterial nodes. Okay, so already we have seen about the introduction of this nanomaterial and all those things. So just we'll reveal what we have studied in the last class, and then we'll move to the preparation method, the synthesis of nanomaterials with the different techniques. So already we have seen nanomaterials which are having the size less than 100 nanometers. We call in the dimension, we call it as a nanomaterial we are going to be called. And nanomaterials are very much interest because of they are having some unique properties in case of optical, magnetic, electrical, and as well as in other properties. So that is the reason why we are studying nanomaterials are very important. And nanomaterials uh, which we are nowadays commercially using, like in the case of what we call cosmetics, sunscreens, as well as this electronics, all these we are using. So that is what very much importance we have. Okay, so the classification of nanomaterials also we have seen, like nanomaterials are having different sizes. They have divided like a zero dimension, one dimension, as well as a two-dimensional, three-dimensional nanomaterials we have seen. So then these are the what we call different types of nanomaterials. Zero dimensional will be in this form like spheres and clusters we have. In case of a one dimensional, we have like a nanorods, nanowires. In two dimensionals, nanofilms. And in the case of the three dimensional, we have a nanoparticles like these we have. So then uh, we said the different type of nanomaterials we have seen, like generally these are two categories we have. One is full rings and another one is inorganic nanoparticles. So about that we have seen already in the last class. So then we have like different types of what we call carbon nanotubes we have. And carbon nanotubes structure is like this zigzag, chiral, as well as the arm shape we have. Then we have seen that single uh, walled carbon nanotubes we have seen, and the multi-walled carbon nanotubes we have seen. So like this, so this is the what we have single walled carbon nanotubes. This is a multi-walled carbon nanotubes which we have. So generally the single layer carbon graphene you are going to be have in the case of the SWCNT. And in the case of the multi-layer, in this case, multi-walled carbon nanotubes, we have multi-layer. So as we seen that some what we call comparison of the single-walled nano carbon nanotubes as well as the multi-walled carbon nanotubes we have seen. Then we'll move to next one, that is synthesis of carbon nanotubes. So we'll study about the synthesis of the carbon nanotubes. So now uh, there are what we call different methods are there. Otherwise, we can say that different techniques are there in order to synthesize nanoparticles. Like different methods, like what we call we have like a physical method is there. 1 minute. So we have like different techniques in order to what we call synthesize the nanoparticles. We have a physical method is there, chemical methods are there, as well as the biological methods, and we have like a self-assembly techniques. So these are the different techniques we have. Okay, so among these synthesizing methods, so in general, we have like a two types of approaches in order to form these nanomaterials. So generally we have like a top-down method as well as the bottom-up method. So in the case of the top-down method, if you take, so this top-down method, it will take like a size reduction from bulk materials you are going to be have. Whereas in the case of the bottom-up method, In this case, materials will be synthesized from atomic level. So from low level to high level, it is going to be synthesized. And in the case of the top down, it is synthesized like a size reduction from bulk material. So from bulk, we'll take the bulk materials and we are going to be make small nano materials we are going to be take. So that is what you have different types of nanomaterials we have. Then uh, if you see this one, so like this, in the case of the what we call the different methods, general methods we have. One is a top-down method. So it is shown in this figure, top-down method, and it is in the form of bottom-up method. So in the case of the top-down method, we will take a bulk material metal we are going to be take, and with this bulk metal can be reduce the size like powders, which is having the size of less than 550 micrometers, and that can be what we call converted into nanoparticles. So this is what we call it as a top-down method we are going to be called. And whereas in the case of the bottom-up method, we make small atoms we are going to be take combined means different atoms we are going to be take, and these atoms will make a form as a clusters we are going to be formed, and from that we will make this nanoparticles we are going to make. So these are the in general methods. Top-down method is there as well as the bottom-up method. So in these in general method, like whatever the methods which we have said that like physical methods, so we have chemical methods as well as the biological methods. So some biological methods comes under top down, some comes under the bottom up method, whereas in the same in the case of the physical method, in order to synthesize nanoparticles, and as well as in the case of the chemical methods also, both physical as well as chemical methods, some will come under the top down method as a method, and another some of them comes under the bottom up method. So this is what in general method we have top down method. From bulk material we are going to take, that will be converted into nanoparticles in top down method, whereas in the case of the bottom up method, we will take atoms and we'll make the clusters, and from that we'll form these nanoparticles we are going to be formed. So this is what in general methods we have. Then after, if you see synthesis of these carbon, sorry, nanoparticles, if you take. So these synthesis of nanoparticles uh, classified as I told that top-down method. So in the case of this top-down technique, whichever we are using in order to make this what we call nanoparticle, the starting material will be always it is in the form of a solid state you are going to be have. So this is what you have to note down. In the case of the top-down class technique, where we are preparing what we call nanoparticles. So mostly the starting material will be solid state material you are going to be have. And if you come to this bottom-up technique, so in the case of this bottom-up technique, the starting material is either in the form of a gaseous state you may be having, or in the form of a liquid state we are going to be have. That is what some difference will be there in the case of the top-down method. The starting material is solid state, whereas in the case of the bottom-up method, we have like a gaseous state or a liquid state we are going to be have. So that is difference which we have in the case of this top-down method, and as well as the what we call bottom-up method, whichever we have. And the next one here we'll see what we call the method synthesis of nanoparticles methods. So if you see, like already we have discussed about the top-down technique, bottom-up technique. So in the case of the top-down technique, so generally one method which we are going to be get is mechanical grinding. So which we will be calling it as a ball milling technique, which we are going to be study here. So this is comes under top-down technique we are going to become. And in this top-down technique, we have a what we call lithography. So this is also comes under this top-down technique, and as well as this etching technique or erosion technique. All these techniques come under the top-down technique we are going to be get. And if you consider this what we call bottom up technique. So in the case of the bottom up technique, if you see the sol gel method, So this will comes under bottom-up technique. So generally in the case of the sol gel method, we use mostly liquids. We are going to be use in order to form this what we call nanoparticles. So this chemical vapor deposition method. So this chemical vapor deposition method also what we call it is a bottom-up technique. We have a physical vapor deposition method. This comes under bottom-up technique, as well as the electrochemical deposition, hydrothermal method, as well as the this what we call atomic layer deposition. All these comes under this what we call atomic layer deposition. All this comes under the bottom-up technique. So these are the some different methods to prepare under top-down technique, as well as the bottom-up technique. Okay. So now next we'll move to the physical method we are going to be discuss. Uh, Physical method. So in the case of this physical method, which we have is a what we call first one comes under physical method. You are going to get this ball milling method. So which ball milling method is also known as what we call mechanical grinding. We are going to be called. So either mechanical grinding or ball milling, both they comes under what we call this top-down technique. They are going to be get. So this is a physical method. So under this physical method, which we have studying ball milling method. So in this case, what we'll have is this ball milling method. If you take, this is a high energy ball milling is one of the simplest top-down method. So this comes under ball milling method comes under the top-down approach. This is a top-down approach which we have, this ball milling method. And in this case, by using this ball milling method, by the top-down approaching of method, which we make a nano powder of some metals as well as the alloys. Okay. So by using this, we will make what we call uh, some metals as well as the alloys. So nano powder of metals and alloys we can make with the help of this ball milling method. So in this case, if you take metals or alloys, we have like a what we call a steel or what we call a tungsten carbide. So some metal which is a hardened steel. Generally, we are going to be called which is a hardened steel. So these are what we call we have like a uh, tungsten carbide. This is a alloy we are having. So these hand steel or tungsten carbide balls are used in different sizes. So the balls means the shape of this hardened steel will be the form of the ball you are going to be have, and the shape of this tungsten carbide you are going to be having the shape of a ball you are going to be have, and these of different sizes we are going to be use. These different sizes of balls of containing what we call containers, depending upon the required quantity we are going to be take here. So generally, the powder or flakes of less than what we call 50 micrometers. So less than 50 micro meters. Okay, less than 50 micrometers of different materials are put into this container. So put into this container we are going to put here. So generally, the mass ratio of balls is taken. Mass ratio of the balls will be taken in the ratio of the 2:1, and the container is less than half filled. Generally, the container will be less than half filled to enhance the efficiency of the milling. So we are not going to be take all these either these tungsten carbide balls or hardened steel balls. If we take example, so we are not going to be fill completely. So generally, what we'll do is we are going to fill half only here, and then we'll start grinding here. So then after filling this half, filling this either tungsten carbide balls or hardened steel balls, what we'll do is we'll close this one. We'll close this one. So after closing the container or the containers which are allowed to rotate this is allowed to rotate at high speeds. Okay, it is rotate at high speeds. High speeds means in the order of what we call some few hundreds of RPMs, few hundreds of RPMs. That means it is going to rotate per minute some 100 times or 200 times, like that, 200 times or 300 times, whatever it may be. So this is going to be rotate here. So whenever you see like this, you are going to be have inside all these you are going to be have. So these flakes are what we call hardened steel balls or tungsten carbide balls, whichever we are going to be placed in that one. So they will be crushed in this what we call in this balls. Okay, so they are going to be crushed in these balls, and they will be after crushing, they will become the size will become less, and then they are going to be formed what we call slowly the size of that is going to be decreases. So generally these are going to be rotated. So generally they are going to be have a horizontal axis. They will be rotating on its own axis. On its own axis, they are going to rotate. So whenever they are rotating, these balls will come and fall into this one, and they will be making into smaller in size. Okay. So after closing this container, what we'll do is we will be containers, whichever we are going to be have, this will be rotated with high speeds. As I told that maybe around 100 or 200 RPMs or more than that, it is going to be rotate. That means rotations per minute will be like 200 or 300. So it is going to be have. So whenever it is rotating on their own axis, what we call with or some central axis, therefore these are going to be what we call planetary ball mills. We are going to be called. So heavy milling balls increases the impact energy on collision. The container may be filled with the air or inert gas. Generally, the container may be filled with what we call air or inert gas. It is going to be filled. So larger balls are used to produce what we call a smaller grain size, but larger defects in these particles is going to be takes place. Larger defects you are going to be takes place whenever we use larger balls whenever we are going to be used. Okay, so this is how in this technique, ball milling technique, we will be taking like a bigger means what we call a size of that will be bulk material size we are going to be take. So in the case of the top down method, as I told that it will be having a larger size, and it is going to be get a smaller size you are going to be get here. So like this, these are going to be form nanoparticles you are going to be formed. Okay. So if you take this ball milling method, so in the case of this ball milling method, we have what we call some advantages. We have some advantages when we using this ball milling method. Okay, so right. So we have some advantages when we use this ball milling method. Uh, so what are the advantages we have here? It is some metals and alloys like what we call CO or chromium or wolfram or these metals. Otherwise, some alloys like aluminum, ferrous or nickel, titanium or what we call silver, iron. So etc. etc. Some metals or alloys whenever we are going to be take. So different types of metal oxide nanoparticles such as what we call Al2O3. So Al2O3 nanoparticles. Okay, Al2O3 nanoparticles or SNO2 nanoparticles or TiO3 nanoparticles. Otherwise, FeO. Otherwise, we have like a Fe2O3. So all these are synthesized using this ball milling method. Okay. So when we take metals and alloys like what we call as cobalt, chromium, W wolfram or aluminum ferrous or silver ferrous, whenever we are using different types of metals, oxides, nanoparticles such as what we call Al2O3 or SNO2 or BaTiO3 or iron oxide FeO and Fe2O3 are synthesized using this ball milling method. Okay. So, with the help of this ball milling method, like a few milligrams to several kilograms powder can be synthesized. So, when we use this ball milling method, the what we call the material which we the nanoparticle which we can make in the range of what we call some from milligrams, okay, some from milligrams to what we call some kilograms, okay, in the range of these milligrams to kilograms. Nanopowder can be synthesized in a very short time by using this ball milling method. So this is one of the advantage which we have when we use this top-down method, ball milling method. When we will have this one. So this method can also be used to make what we call a variety of carbon-based nano materials. So carbon-based nanomaterial means already we have discussed like CNTs, like carbon nanotubes. Okay, so with the help of this, we can get that. So that is about ball milling technique and as well as the what we call advantages which we have in the case of the ball milling technique. And as well as if you take some limitations or drawbacks which we have in the case of this what we call ball milling method. So what is the limitations or drawbacks which we have is so although this what we call a ball milling method, which is a what we call a which is a uh, very simple method for synthesizing nanoparticles. Uh, but there are what we call some impurities will be arising when the rotating balls and their inert gas also. Okay. So the drawback which we have in the case of this, otherwise we can say that some limitation which we have in the case of this what we call ball milling method is it is very simple method for synthesizing nanoparticles, but there are some impurities will be arising from the rotating balls and due to the inert gas. So that is what some drawback which we have in the case of this one, what we call ball milling method. So this is about ball milling method. It is very important, which we have. Okay. So next we'll move to another method, synthesizing of nanoparticles, which we have. So which we have is a what we call physical vapor deposition method. So we'll see here this physical vapor deposition method. So in the case of the physical vapor deposition method, so which describes this physical vapor deposition, which describes a variety of vacuum depositions technique which can be used to produce what we call thin films. Okay, so by using this one, so we can produce what we call thin films, and what we call thin films and coatings on a substrate, and coatings, coatings on substrate, coating on substrate. So this uh, physical vapor deposition describes a variety of vacuum deposition technique which can be used to produce thin films and coatings on a substrate. So this is what we can be used by using this physical vapor deposition method. So if you take this physical vapor deposition method, so this physical vapor deposition method is a dynamic bottom-up method which we have, bottom-up synthesis technique, which is capable of producing what we call thin films or thin film materials, which are having the size of in between what we call 1 to 100 nanometers. So in between 1 to 100 nanometers, whatever may be the size which we required can be produced with the help of this what we call physical vapor deposition method. So generally, which we are going to produce is a thin films materials we are going to produce here. So in this way, what we call physical vapor deposition, the material is heated above its melting point generally. The material will be heated above its what we call melting point to generate what we call vapors. So which are then deposited on the target surface here. The target surface here at this point, whichever we have. So this is the target generally we have. So here we have the substrate. So which will be deposited on the target surface. So thermal evaporation here we are going to be take here. So the thermal evaporation which involves the heating a source. So generally which we have a source, it is going to be heat the source above its melting point in order to extract atoms from it. Okay. So in this physical vapor deposition method, so using this physical vapor deposition method or technique, a single element with a low melting point, often a metal, can be converted into nanoparticles. So metal can be converted into nanoparticles here. A metal can be converted into nanoparticles. Method can be converted into nanoparticles. However, it is challenging to deposit a consistent combination of two distinct materials because of the variation in melting point. So suppose if you take two different metals, uh, if you want to deposit, so generally we will have two different methods or sorry, two different metals may be having their what to call this melting point is different. So it is very challenging method to deposit that one on what to call target here. So both what we call solids and liquids can be evaporated and produce vapors here. So in this method, as we told that in this case of this bottom up method, whether we will be using liquids or vapors, we can be used. So here we can use like solids we can use or what we call as well as the liquids also we can be used. Okay. So liquids also can be used. Which can evaporate and produce vapors here. So the solid particles are produced by the nucleation and the condensation of the uh, what we call vapor during this cooling process. Okay, so the solid particles are produced by the nucleation and the condensation of the what we call which is vapor during the cooling process. So another one which we have is a sputtering. Sputtering. So sputtering is a process of depositing what we call materials of high melting points via what we call these atoms by the bombardment of source material with the what we call energetic ions, which leads to the generation of the nanomaterials here. Okay. So that is how we will be depositing this nanoparticles at the what we call target material. So the physical vapor deposition method is used to deposit any type of what we call inorganic materials such as metals, alloys, and as well as the organic materials. So generally, this PVD, physical vapor deposition method, is takes place in a what we call vacuum condition. We are going to be take place. So we will be using a vacuum that inside of that chamber we are going to be used. Okay. So if you see the applications of this what we call physical vapor deposition method. So this physical vapor deposition method, generally we will be calling it as a PVD. So this PVD is used to otherwise used in the manufacture of items which require thin films, thin films. So in the case of the application of the application in the thin films, we will be using this PVD physical vapor deposition methods, and as well as these thin films will be utilized for optical, mechanical, chemical, or electronic functions. So the thin films will be utilized in the case of the optical, uh, as well as the what we call mechanical, will be used in mechanical, as well as the chemical applications. Chemical applications are will be utilized in electronic functions. Okay, electronic functions. So these are some applications which we have, like in the case of the which requires thin films for optical purposes as well as the mechanical purposes, chemical as well as the electronic functions will be utilized. Okay, and this PVD is used to make what we call, especially in the case of the physics, if you take here. Right. So this PVD, if you see especially in the case of the physics or electronic applications, if you see, so this PVD is used to make what we call a semiconductor devices. So which are very importance we have semiconductor devices. Okay, semiconductor devices. So semiconductor devices means even in the case of the optical devices, where we can store the data that can be done with the help of these semiconductor devices. So these semiconductor devices, as well as what we call thin films, they can be used as a thin films. So in the application of the semiconductor devices, thin films, it is used, PVD method is used, and as well as the in case of the what we call solar cells, thin film solar cells also, this can be utilized. PVD method is utilized. Okay. And if you see some other applications which we have in the case of the PVD is aluminized PET. That is nothing but the polyethylene terephthalate uh, film, which is used for food packing as well as in the case of the balloons. So that is one application, very useful applications which we have by using the nanoparticles whichever we prepare with the help of this PVD method. And if you take what we call titanium nitride coated cutting tools, okay. So cutting tools if you have which are coated with titanium nitrides, okay. So these cutting tools whichever coated with the titanium nitride, so which will be used for what we call metal working, which is used for metal working. That is nothing but the cutting tools or machines, whichever they have, which they are coated with titanium nitride. So they will be utilized, what we call, otherwise they will be very useful in cutting metals, okay, metal working. We are going to be use this one. So this is what some applications which we have by using this what we call physical vapor deposition method. And if you take some drawbacks or limitations, whichever we have in the case of what we call physical vapor deposition method. So the limitations or drawbacks which we have is this is a what we call if we are getting these thin films, but generally what will happen means sometimes it won't get uniform thickness you are not going to get. That means the thin film whichever we have produced that may not be having the uniformity. Otherwise, we can say that it is going to be get non-uniformity. Okay, non-uniform. The size of that material, whichever we have got, is having a non-uniform. So that is one drawback which we have, and as well as the another drawback which we have is line of what we call some shadowing you are going to get. That is one more drawback whichever we have, and another drawback which we have is it is difficult to evaporate materials with low vapor pressures. So that is as already I told that if you are using any alloys, so these alloys are having different what we call melting points. So in order to melt those alloys, some it will take some what we call some difficulty we are going to get. So that is one drawback which we have. So that is materials with low vapor pressures also. It is very what we call difficult to evaporate. So with which are having the low vapor pressure. So this is about the physical vapor deposition method, which will be used what we call in order to prepare this nano particles or nano materials which can be synthesized. So these are some drawbacks as well as that applications which we have seen here. Okay. So next we'll move to another uh, type of this one, which we call it as a ionized cluster. Okay. Ionized cluster beam deposition we are going to be called. So it is useful to obtain what we call adherent and high quality single crystalline thin films. So by using this method, we can obtain, otherwise we can get what we call single crystalline thin films. So single crystalline thin films can be done with the help of this what we call cluster beam deposition method. So this setup, which is consisting of what we call, it is having the source of evaporation. So in this, it is consisting of source of evaporation will be there, and as well as the nozzle, it will be there through which material can be expanded into the chamber. And we have another one. The part which we have is a electron beam. So electron beam will be there to ionize the clusters, and we have an arrangement to accelerate these clusters, and we have a substrate on which a nanoparticle film can be deposited uh, in the chamber. Okay, so these all are what we call will be there in a uh, some chamber will be there. Otherwise, all these are housed in a suitable vacuum chamber. So you'll be having the vacuum chamber for this ionized cluster beam deposition. In that, all these, whatever we said, that like a source of evaporation, nozzle, or materials which we can expand into the chamber, all otherwise electron accelerators, the clusters, all these will be there within the house of this what we call vacuum chamber we are going to be have. And after that, the small clusters from molten material are expanded through fine nozzle. So in this one, the vapor pressure whichever we will apply in this will be in the order of what we call 10 to in the order of around 10 towers we have, otherwise 10 to 2 towers whichever we have. So 10 to 2 or 10 to 2 towers we are going to be apply here, the vapor pressure. So which will be created in the source, and the nozzle which is having inside nozzle needs to have a diameter generally larger than the mean free path of atoms or molecules will be there in vapor forms in the source to form what we call these clusters. Okay, so then on collision on collision with electron beam clusters get ionized. So this will be get ionized on collision with the electron beam clusters get ionized. So due to applied accelerating voltage, which means we will be changing the voltage. It is possible to control the energy with which the clusters hit the particular substrate. So thus it is possible to obtain the films of nanocrystalline materials using this ionized cluster beam. So this is what about ionized cluster beam we have. So next we'll move to another type of methods which we call it as a what we call another method. Uh, Previously we have seen physical methods which we used to what we call which we used to make this nanoparticle synthesization. Next, we'll go for the next method, which we call it as a chemical method. Under this chemical method, we have what we call sol gel method also is there. Sol gel method comes under this what we call chemical method we are going to get. So in the case of this sol gel method, so sol gel method is a what we call chemical process. So it is a Soldier method, if you take, so this soldier method is a chemical process. It is a chemical process which is used to make what we call ceramic and glass materials. So soldier is a chemical process which is used to make ceramic and glass materials. So chemical process which is used to make what we call ceramic as well as the uh, glass materials. Okay, glass materials used to make this ceramic and glass materials in the form of thin films, in the form of thin films, as well as the what we call in the form of a fibers you can make, or in the form of a powders you can make. So by using this chemical method, the method which we are using is a sol gel method we are using. So this sol gel method is a chemical process which is used to make what we call a ceramic as well as the glass materials in the form of what we call thin films, and in the form of a fibers as well as in the form of powders. That is nano thin films. We have a thin film itself, it is a nano thin film, as well as the nanofibers we'll be making with the help of this sol gel method, and as well as the nano products also we can make here. Okay. So here we will be calling it as a sol gel method. So generally a sol whichever we have, it is a colloidal or a molecular suspension of solid particles of ions in a sol we have. And a gel whichever we are going to be have. So a gel is a semi-rigid mass we have that forms when the solvent form the sol begins what we call evaporate, and the particles or ions left begin to what we call join together in a continuous network here. So a sol is a colloidal or a molecular suspension. It is a colloidal generally. It is a colloidal or molecular suspension of a solid you are going to be, solid particles you are going to be have of ions, solid particles of ions you are going to be have. And then this gel is a semi-rigid, it is a semi-rigid mass you are going to be have. Okay, that forms when the solvent from the sol begins to evaporate, and the particles or ions left begin to join vertical together to continuous network it is going to be have. So generally, this this soldier process consisting of vertical first one which we have here, it is this soldier process consisting of first one is the desired colloidal particles will be consisting of desired colloidal particles, desired colloidal particles we have, which is particles one dispersed in a liquid to form salt, okay, which is dispersed in a liquid to form a salt. And second step which we have here, it is the deposition, okay. So the deposition which we have. So this deposition of a salt solution produces a coating on the substrate. So the deposition of solution produces the coatings on the substances. Next we have is the particles in the sol, the particles. So the particles in the sol are polymerized through the removal of stabilizing. Okay. uh, to the removal of the stabilizing components and producing gel in a state of continuous network. So this is what the particles in the sol are polymerized through the removal of stabilizing components and producing gel in a state of continuous network you are going to be have. Next one, next one which we have is the final heat treatment. In the final heat treatment, uh, the final heat treatments, the final heat treatments. Okay. The final heat treatments, they what call pyrolyze the remaining organic or inorganic compounds and form an amorphous or crystalline, what call they form amorphous in nature, amorphous or crystalline or crystalline pooling sol gel formation occurs here. So, which is in hydrolysis or condensation or groups of particles, and what we call they are going to be formed these. Okay, hydrolysis or condensation, a group of particles, they are going to be formed here. So this is about the sol-gel method, which is utilized in order to make what we call uh, in order to make this uh, nano size nanoparticles will be synthesized. Next method, which we are going to see here, in the case of this chemical methods, is another one which we have is a hybrid method, which we have is a hybrid method. 1 minute. We are going to be study about hybrid method. Hybrid method. Okay. So in this hybrid method, hybrid materials are composites, hybrid materials whichever we are using. So hybrid materials, hybrid materials, they are generally are they are generally are composites we have. They are composites. Okay, they are composite which consisting of two constituents at the nanomaterial molecular level. Okay. So hybrid materials are composites consisting of two constituents at the nanomaterial molecular level. Okay. So the commonly one of these compounds is which we are using in this hybrid method is inorganic, and other one is organic nature you are going to be have. So like a hybrid means which is consisting of two or more you are going to be have. So in these, the compounds whichever we are going to be have is one is a combination of inorganic compound, okay, inorganic, and other one is a organic compound. So one is a inorganic compound you have, another one is a organic compound which we are using in this hybrid method. Okay, so they differ from traditional composites. In the method which we are using, hybrid method. So they differ from traditional composites where the constituents are the macroscopic. So macroscopic means either a micrometric you are going to be have, micrometric milliliter level you are going to be have. So mixing at the macroscopic level leads to what we call a more what we call homogeneous you are going to be have. Okay. The process of depositing materials directly from what we call PVD, physical vapor deposition, uh, comprises. So in this, as I told that the what we call mixing at the microscopic scale leads to more homogeneous materials that form what we call characteristics in between the two original phases, are even new properties you are going to be formed here. Okay, so in the hybrid nanoparticles, they are expected to have larger applications. They are having larger applications in the case of the biomedicine, the application of these materials, whichever formed with the help of this hybrid method. So they are having the applications in the field of what we call applications in the field of biomedicine, the field of the biomedicine they have, and as well as in the case of the antibacterial and antibacterial, and they can be in the case of applications in the biomedicine field you have, in the case of the antibacterial we can be make with the help of this hybrid method, and another nano particles whichever they have synthesized by using this hybrid method, so they will be utilized in the case of the what we call energy storing devices in electronics. That means we want to store more amount of data, so this hybrid method will be followed to make this energy storing devices in electronics, and as well as they will be utilized in catalysis, then what we call single nanoparticles. So in general, the what we call the method whichever we are using in this case uh, would be classified into two main categories. One is a physical as well as the chemical method is there in this one. Okay. So as compared to the chemical methods, the process for the synthesis of hybrid nanoparticles by physical methods are simple. Whereas in the case of the chemical method, wherever we are using, so that may be somewhat complicated as compared to the physical method here. Okay, simple, but the control of the size of the hybrid nanoparticle seems to be complex. Okay, the size whichever we are going to be get here, so it may be complex. Means the size of the particles, that is the nanoparticles which are formed by this hybrid method, to be complex you are going to be have. So regarding the dimensional synthesis, especially the what we call nanostructural, they are expected to provide better performance than the obtained from the physical method. Okay, so the nanoparticles, whichever the application wise, if you see, so the particles whichever they have synthesized with the help of this what we call chemical method, they are having more applications than the what we call whichever they have been formed with the help of a physical method. Okay. So in the physical preparation methods, the individual nanoparticles remains sometimes separated and distinct within the what we call final nanostructure. Okay. So however, what we call the stronger hybridization between the nanoparticle is often obtained by this pathway, while the nanoparticles prepared by chemical method can exhibit unwanted properties. So that is one drawback which we have with the help of what we call this chemical method which we used in the hybridization. So physical method is having somewhat advantage than the chemical method. Okay. And if you see what we call due to the presence of chemical species such as what we call stabilizing ligands, polymer shells, it is going to be difficult in the case of the chemical method which we use in the hybridization method. Okay. So different methods have been employed for the fabrication of hybrid nano carriers depending upon their what we call chemical composition and applications. Okay. First, a two-step approach process in which the uh, outer shells are prepared separately and then the what we call combined for the formation of hybrid nanoparticles. Okay. First approach is that one we have. The second approach is the single step in which the various state of the art techniques of the assembling method is incorporated in order to prepare this hybridization method. Okay. So this is about the hybridization method, which will be used in order to make this nanoparticle. Okay. So the single step method is there another one. The single step method is applied when the what we call core materials such as polymers, organic substances are made to form the drug. Okay, so that is about single step method we have, which will be utilized in order to make this uh, nanoparticles. Okay, so another methods which comes under this chemical what we call methods in order to prepare these nanoparticles. So one is electrochemical electrochemical method. Okay. So and the chemical vapor deposition method, which we call it as a chemical vapor deposition method. This also comes under the chemical methods, and as well as the another method which comes is under this one is electrode position. Okay, electrode position. This also comes under chemical method in order to prepare nanoscale materials. So can in this electrode position, it is used to electroplate a material in many liquids called as electrolytes when it is passed through two electrodes which is immersed inside the electrolyte. Certain mass of substance certain mass of the substance liberated at one electrode gets deposited on the surface of the other. So by controlling the current and other parameters, it is possible to deposit even a single layer of atoms in the case of this electron deposition method. Okay. So generally, mostly the films which are having here will be of a copper, nickel, Rm, etc. You are going to be have can be produced by this electron deposition method. Okay, the films thus contained are mechanically robust and they are highly flat uniformity you have. Okay, so these are about some methods synthesis of the what we call nanoparticles by using different methods we have seen. So starting from, if you see, so we have seen physical vapor deposition method we have seen, and then we have seen the chemical vapor deposition method we have seen. Under those, we have different types of methods like what we call sol gel process we have, and another types of methods we have seen. So this is about what we call methods in order to make okay. So in the next class, we'll see about another um, methods